So I'm going to talk to you about competition among pricing algorithms. Really, this paper is a response to what we've seen in the literature. It's a joint with John Asker from UCLA and Chaim Fershtman from Tel Aviv. So the question we want to ask is, how did the design of competing AI pricing algorithms influence the competitive outcomes realized in markets? So let me say, as a sort of start on this, one of the topics industrial organization more generally has not gone on top of what is the pricing by platforms, and platforms are becoming much more important in the economy, and we should be doing something. So I think much of the literature, the reaction, so there has been there was a couple of papers, which I will come to in a second, that started looking at this and came to certain conclusions, okay? And this brought on a bevy of activity by the regulatory agencies in different countries, okay? So, this is Margaret Vestager in Brussels. The challenges of automated systems create are very real. If they help do price fixing, then there's a problem. The CMA is a competition and market authority in London. Similar kinds of things. The ACC is in Australia, and actually in London I talked to the guy who's in charge at London at the Competition Market Authority, who, by the way, is an economist. We were just talking about this at lunch. It's the first time we've ever been to a regulatory agency that didn't have a lawyer or a politician on top. This guy has a PhD from Stanford. And he just hired 20 computer scientists to investigate this. Okay, so maybe it hasn't hit the profession very much, but it's hit the regulatory authorities quite strongly. Okay, so there has been a literature in economics. The paper that maybe started a lot of people thinking about this is this paper in the AER 2020. And then there's been some empirical papers, Brown and McKay on pharmaceuticals, and Assad and a bunch of other people on gas stations. I think what you really want, I'm going to talk more broadly about this than just my paper. So I think what you really want to know is how they write the algorithm. Certain aspects of how the algorithms are written. Okay? The problem for an empirical person is they're proprietary. None of these firms that write the algorithm are going to tell you how they wrote the algorithm because they're selling them. Okay? And so the empirical papers here, they're trying to figure out, maybe not the way it's not, the way you really could do something is you would try and figure out which algorithms are consistent with the results that you see in the data, okay? And there's a start on this especially in the Assad paper. Harrington has a thoughtful review on competition issues. He usually is very thoughtful about these things. There's a bunch of other papers, and that's without even going into the computer science literature and the mechanism design literature. So there's a whole other set of literatures that I'm not even going to touch on. And there's a theory literature on learning and games, which I will touch on, but just briefly. Okay. Here's the topics I want to talk about. I'm going to talk about the learning rules in an algorithm, okay? And I'm going to distinguish between synchronous and asynchronous. What a learning rule is for an algorithm, the algorithm chooses a policy, there's an outcome, okay, something happens, he gets profits, doesn't get profits. He uses that, the algorithm has something built into it that uses that outcome to update the value of the policy. Okay, that's what a learning rule is for an algorithm. Okay, so I'm going to look at different learning rules, and then I'm going to look at two different other aspects of it. Most of the work in these papers is what I call offline. It's training a computer algorithm to do stuff, okay? Offline stuff, training stuff is essentially costless. It's just running a computer, okay? And these, for Amazon, running a computer is not a big deal, okay? On the other hand, if you go online with the same thing, okay, experimentation is costly because you're not choosing the right price. okay? And there's an experiment, there's an exploration versus experimentation trade-off, and it's complicated. Why is it complicated? It's because at the same time you're exploring and doing this, the other guy's doing it also. Okay, so the standard single agent exploration versus exploitation is not here, okay? It's a different problem, okay? Then I'm going to talk about convergence of offline policies, and I'm going to talk about online outcomes using offline policies, okay? So, and then I'm going to talk about the choice of learning rules, and I'm going to talk a little bit about collusion, okay, at the end. Okay, so how do these things work? There's some coder, okay, and what the goal of it, he has to set what he wants to do. What's the goal of the algorithm? I'm going to say it's the maximization of expected discounted value of net cash flows, okay, that's standard I/O. He's going to have a feasible set of actions. In our case, it's going to be price, and it's going to be in some feasible set of prices. There's going to be a set of states or information sets which the algorithm can condition on when it makes its choice. So it knows something, okay, makes its choice. So in our case, when we do dynamics, I'm going to say he sees the prices in last period. Okay, so this gives you back to the repeated games literature, okay, in economics. You could choose other things. The coder also has to set an initial discounted value, an initial perception, the machine's perception of the expected discounted value of playing price P at state S for any P and any S, okay? Because it has to start somewhere, okay? And then it needs a rule for choosing price, okay? So I'm at some state, I have a rule for choosing price. It's usually what's called by the CS literature the greedy policy, the maximum. You choose you're fixed at S, you choose the maximum WP, okay? If you're doing experimentation on top of that, there's two ways to do experimentation. I'll tell you about that in a second. You do what's called epsilon greedy policy. So epsilon greedy policy is I choose the maximum with probability 1 minus epsilon, and I choose a random number on the other set with probability epsilon, okay? And then he needs a learning rule, which uses the information generated by the market outcomes to update its perceptions of the values, okay? So, good. I don't know. So starting from initial state, the algorithm chooses a price, play occurs, profits are determined. The information the algorithm observes from play is used to update the state it's in, okay? And its perceptions of the expected discounted value from the state it was in at the start of the period. Because it got an outcome from that state, he wants to update that state. So it can update only the value of the action it did take. It sees the profit from that action, okay? Or it can also have a model of what the profit would have been had it chosen a different price at the state last period. Okay? Okay. I'm going to do everything I need to do today. I can do it in the most simple model you can ever think of. So I'm going to do n equals 2. And then I'll show you what generalizes. Okay? Okay. The updating rules are basic, okay? How the algorithm learns is the most basic thing about it. So there's an iteration of the algorithm. So now I'm going to do training, okay? So I'm going to train the algorithm before I use it online, okay? After iteration K, the algorithm updates one or more of the WK PSIs, okay? So if it's not updated, so if I don't update, so I don't update any state other than the state I'm at. That's not necessary, by the way. You could use neural nets or something, but I'm going to do it that way, okay? So the only thing I could update is at the state I'm at, I could update all the P's at that state, okay? But if I don't, then the WK plus, so if I don't update that P, it's WK plus 1 is just WK, okay? So the learning rules, there's two things that limit the feasibility of it. One is the information the algorithm gets on the competitor's play. I can't condition on P minus I if I don't see P minus I. Okay, if I don't see the actor, okay? So sometimes you'll see it and sometimes you won't, okay? And then there's market-specific knowledge that the algorithm might have or might build, okay? So what's market-specific knowledge? It could be the demand system. So if I know the demand system and my costs, Is that clear? I can predict what would have happened. And if I see the other guy's price, I can predict what would have happened had I chosen a different price, okay? So that's the kind of market information. You can use less market information. You might not know demand, but you might know that demand slopes downward. That's enough for many things, okay? Okay. So there are two extremes of updating. One is what's called, so these words are pilfered from the computer science literature. They use them in a slightly different context, but they're very similar in knowledge. So asynchronous updating, the algorithm only observes its own profits and doesn't use any information on demand. So the only thing it updates is its perception of the price, of the value of playing the price it played that period, okay? And then the extreme other one is perfect synchronous updating, where I know the demand system and I can predict every price, okay? I can use every price, okay, good. Okay. So the literature before us was focused on converged policies. Okay, so just standard definitions of convergence. An AI pricing algorithm has converged at iteration k star if policies don't change for k greater than k star. That is, the W don't change. Okay? A recurrent class of states of a Markov process, you guys probably know. I don't know how much you know and how much you don't, so I'm going to start. And you can tell me if I'm going too slow. The recurrent class of states from a Markov process is a set of states that are visited repeatedly. Okay, so in math terms, infinitely often. Okay? So it can be that this process will converge to a recurrent class, a subset of the states, and it hits every point in that subset all the time, all the time, infinitely often, okay? Or it can converge to a point, okay? If it converges to a point, we call it a rest point, okay? So a rest point just says, if I've reached a rest point after some k star, prices are constant thereafter, okay? So when the recurrent class, actually I don't really have a formal proof of this, but typically, okay, when the recurrent class is not a point, okay, you'll see cycles in the recurrent class. It'll go from one point, from point P1 to P2 to P3, then back to P1 to P2, P3, and you'll see this in the outcomes that I'm going to show you. So we talked about experimentation. There are really two sources of experimentation in these algorithms. If you were to look at the CS literature or the reinforcement learning literature, they're going to, when they start an algorithm or when they start a training algorithm, they're going to start it very high, with very high W's for all prices. Why? Because that way you learn, they'll come down and then you'll try another one. So this is trying to guarantee that you've explored all possible policies. If I start very high, okay, you're going to end up exploring a lot. Okay, so that's one way of exploring, okay? It's computer intensive, okay? Another way of exploring is what I said at the beginning. You can do epsilon greedy policies, okay? Typically, in this literature, epsilon is epsilon of the iteration, and it goes to 0 as the iteration gets large, okay? So the cardinality, the size of the state space, okay, is not a theoretical concern. That is, it just doesn't matter to me. I'm going to assume it's finite just because I don't want to do heavy-duty math, but it doesn't really matter, okay? But it does have two practical implications, okay? So one implication is, if you have a ton of states, you're going to get a small number of outcomes per state, okay? And the precision of the estimate depends on the amount of outcomes per state. Okay, so so from the point of view of a training algorithm, if you have a big enough computer power, it doesn't matter very much. But from the point of view of using the algorithm online, it matters. Okay, because precision will kill you. Okay, it's going to be costly if you make an error. That's okay. So that's one thing. An algorithm with a lot of states has to keep more in memory also, so you need a bigger memory, okay? again, for training algorithms, I could be problematic, okay, but I'm not going to worry about it. Okay, let me give you the simplest case first, and then go on to a more complicated case. Maybe I do need the water. The simple case, asynchronous algorithm. The thing about asynchronous algorithms is they're model free. You know, you play a price, you see the profits. That's it. That's all you need to know. Okay. It only requires observing its own profits. Okay, and it doesn't need any other information. And the way you get WK plus 1 is, does this work? Yes. It's, you just take a weighted average of what profits you got today and the and what you came in with, what your perception was when you came in with. Okay. So often, by the way, if you were a serious CS guy, you'd let the alphas have not change over the iterations, because the early iterations are less precise than the later iterations. But the rules of convergence, it doesn't matter. Okay, so I'm going to forget it. Okay. By the way, this literature all starts with a 1956 article by Robbins and Monroe, which is the simplest article you could possibly imagine. It's like 5 pages. You can't miss what they're trying to say. Okay. So asynchronous stuff is WK plus 1 just equals, you know, weighted average of the two. Okay. And if I played P, and if I didn't play P, I don't update at all. Okay. If I'm doing if I'm doing synchronous updating, then I need an estimate of what price would have been at a price I didn't play. Okay? So this, you know, perfect synchronous would just say, I know it exactly. I know the demand system. I know the price you played. I can figure out what my profit would have been from had I played that other price. Okay? Okay, so we'll do that for the most part because that's the extreme. But we'll also do just what happens is I played a price. Okay? I don't know the demand system, but I know that demand slopes downward. So if I would have played a price lower than that, I couldn't have gotten less demand, given your price, okay? And if I played a price higher than that, I couldn't have gotten more demand. And that puts bounds on what can happen, and it's actually very effective. So the reason I say this and we emphasize this is you don't need to know a lot to get a different result than the results in the literature, okay? Downward sloping demand seems like a reasonable thing to assume and to build into an algorithm, okay? Okay, so here, let me start with the static game. Transparent environment, no weight on future returns, singleton state space. Every time we're starting from the same thing, have no memory. 2 firms, 100 feasible prices, 2 forms of experimentation. The initial experimentation, the initial W's are higher than the maximum possible. So you're going to go downwards, okay? And then there's epsilon k, and with epsilon going to 0, okay? And I'm going to give you, we did 100 IID simulations, waited for each one to converge. So this is what you get. Okay, the top one is asynchronous updating, and the bottom one is synchronous updating. They're pretty different. Okay, the synchronous updating gets to a Nash equilibrium and gets there very fast. The asynchronous algorithm, the Nash equilibrium in this game, by the way, is 2 or 2.2 or something like that, okay? So the asynchronous algorithm gets to a price which is 4 times Nash equilibrium, and it stays there, okay? So this is just to drive home this thing that the way you build the learning thing matters, okay?
So how are the prices generated that are used for the asynchronous updating?
Can't hear you.
How are the prices generated that are used for the asynchronous updating? It's like historical data.
No, the coder sets a price. You start with the W0, okay? Each guy chooses the price that is the maximum of the W0s, okay? The other guy does the same thing. You get an answer. You update the value from that price, okay? Because now I've got my initial condition and 1 observation. I just take an average, okay? And I keep doing that, okay?
It's still online.
It's still offline. I don't know what you mean by online. It's a training algorithm. So there's a computer doing this. We're not actually playing against somebody. We have 1 computer over here, 1 computer over here. They don't talk to each other. Okay? They're both doing asynchronous learning. Go ahead.
I think the question was, what's the data generating process for the data that
No, there's a demand system and a cost system. It's just standard. So there's a demand system and a cost system. You set a price, the other guy sets a price. You each get profits. In this case, I think underneath this one, we've done it many ways, but I think the one I'm showing you is the simplest one, which is national prices, and the guy gets everything. If you're a lower guy, you get everything. And is that what you're asking, Max?
I guess I was just wondering if the opponent, like, if there's kind of a best response.
There's no discussion between the two computers. There's never going to be any discussion, okay?
The opponent is not going to...
He's doing a best response to what he thinks you will do, or what he thinks the outcome will be. He doesn't necessarily even know what you did. He could know what you did. That, in synchronous, you need to know what you did, okay? But he doesn't even, he's just playing a best response to what happened in the past when you played P, okay? So I played, okay, and that's what the experimentation is doing. You know, it's trying to figure out, you know, it's the standard thing where sometimes you want to play the thing that's greedy, you know, that does the best, that you think is the best, but you also want to explore because you don't know what happens at the other price. Okay, so it's just standard. The difference is that now there's two guys doing this exploration versus exploitation trade-off. That's the only difference. Okay. Okay, you can actually work out, there's a paper and proceedings paper by the three of us, which it's very simple, but you can prove the following proposition. If we just stick with the static game to make it extreme, okay? If the AI algorithm uses synchronous updating and greedy policies, okay, and the two algorithms choose a pair of prices which is a Nash equilibrium, they're going to stay there forever. Okay, it's almost obvious. And any rest point of the algorithm must be a Nash equilibrium. So that's synchronous updating. Okay? If you're doing asynchronous algorithm and you have a rich enough initial distribution of initial conditions, you can converge to any price in the support with just the appropriate random draws. Okay? Okay. This proposition is true regardless of the number of firms playing this game. Okay, regardless of the demand function, it's straightforward algebra. Okay. Perfect synchronous is extreme, but in the AER paper where we just do the static stuff just to show what's going on, okay, we show that just this downward sloping demand gets you very close to perfect synchronous. Okay, so that's not a lot of information, but what it does do is it assumes that you know P minus I. Because I've got to be able to figure out what the price would have been had I played something different. For that, I need to know what the other agents' prices were. Okay? Okay. So here's the question. Does the asynchronous outcome indicate collusion? You know, my argument is no, there's no scope for history-dependent strategies. So there can't be a punishment scheme. There's no history in the state space, and the AI doesn't care about future payoffs. So this cannot be collusion as we know collusion. Okay? So in the static game, if converged prices lead to excessive prices, it's because of randomness in the program and a simplistic learning rule. That's what's going on. Okay? So this is going to be different. It's going to be more subtle in the dynamic game. Okay, but at least you know where, you know, there is a set. Okay, good. Okay, now I'm going to move on to dynamics where it gets a little more subtle. Okay, the state space is, I'm going to, you know, you could choose any state space. Shouldn't get me wrong, but this is the traditional one used by theorists. You can condition on last period's prices. Okay, so this is a Rupert and Sticchetti, so on. So now history can matter, and in principle, I could get a punishment scheme. Okay. It's going to assume, so this is slightly different from the first case, okay? It's going to assume that the algorithm has access to the rival's price, otherwise I can't condition on it. So even asynchronous guy will know the rival's price. What he doesn't know is the demand system. Okay? Because if I'm going to condition on something, the guy's got to know it. It's got to be in his information. I'm going to discount the future bid equal 0.95, sorry. Okay. It's going to be exactly the same way. Again, I've omitted the K's from alpha, but you can put them back in. So now WK plus 1 equals, I came in with WK. I played something. Okay? If I play something now, I get the profits from what I play, and I get the discounted value, my current perception of what the discounted value will be in the next period, which is beta max y over p wi k, not k plus 1, okay, because that's in memory, okay? And I choose the best y for that at si k plus 1. So that's my current perception, okay, of what the outcome either was or would have been do I have a model for pi e, okay, of what, from my play today, from playing p today, okay, and I'm just averaging it with what my perception was in the past, okay, so there's nothing fancy. Of course, if P equals PIK, then it's just current profits. The pi e is current profit. And if P doesn't equal PIK and the algorithm is synchronous, then the coder has to specify how he estimates this thing. Okay? So one thing we didn't do, by the way, and you could do is you could, at least haven't done TI, you could embody an estimation algorithm in this and try and figure it out. Okay. Okay, so so the thing to note here, which makes it the subtlety in this, to the extent there is one, okay, is in this asynchronous algorithm, you only update WKI, the continuation value. You're updating two things, really. You're updating the profits and the continuation value, okay? So in the asynchronous algorithm, you're updating both of them just at P, okay? In the synchronous algorithm, and this is where it's a little different, you're updating profits for every price. Is that clear? So, okay? But you're not updating the continuation values for any price except for the price that you're played. Okay? So what I'm doing when I do the synchronous algorithm, okay, is I'm updating, you know, I presume the profits for everywhere, but I never actually go anywhere. Okay? So I don't actually go to the following point. Is that clear? So I never go to the following state. Okay? So I don't update that path. Is that clear? Okay. That's the only subtlety in this. Okay? But you can see what's going to happen, right? I'll tell you when we get there. We're also going to use downward sloping demand here. So the interesting thing about downward sloping demand is the algorithm only needs to know, to do downward sloping demand, the algorithm only needs to know what it has in memory from the asynchronous algorithm and the quantities it got at that point. So I have to put one more piece of information, but it's an information that the algorithm should know, because it's the quantity it's sold at those points. Is that clear? Okay, so that's the current profit and the quantity sold. That's all I need to know. And the storage requirements are the same. Okay, and this just tells you how to do it. It's just algebra. Okay, so now let's go to converged policies in an offline game. All of this so far, what I told you about the static game, it was all converged policies, all about converged policies. So it's a training algorithm, okay. They can lead to a point or a set, and they have the two properties, which is it's greedy. Okay, so you always choose the maximum. Okay, and it generates values that satisfy for all p and all s. So all p in p and all s in the recurrent class, in these points that I hit many, many times. Okay, it generates this equation. Okay, which is it generates wi pi p plus the max. That's got to hold for it to converge. Okay, these are the conditions of a restricted experience-based equilibrium in this paper by Chaim Fershtman and I. Okay, it's, you know, I've been using it as a framework for doing empirical work in dynamic games. I can tell you why, because it doesn't require you to know everything in the environment. The states, each agent can have a different state space. Okay, and there can be asymmetric information, and all you do is condition on what you know. okay, which may not be the whole world, okay, which makes empirical work more easy, okay? So that was the reason I was originally interested in this, okay, until John brought up that showed me this paper, okay? It's conceptually, the experience-based equilibrium, it's almost conceptually, it's essentially the same thing as in Fudenberg and Levine's work. The difference is, and the reason never, is they're doing infinite agents. So you randomly meet an agent, and then you update, and somebody else randomly meets an agent. And we're doing, we're doing competition between a finite number of agents. Okay. I never knew that until Susan Athey told me I should look at it. Okay, so what's going on now is only the perceptions of quantities that are updated repeatedly are guaranteed to converge their own true values. You can only have a law of large numbers if this thing is hit many, many times, okay? So you're going to end up getting, for every state in the recurrent class, okay, you're going to get profits right for all the profits if you do synchronous updating, okay? Okay. And you're going to get the continuation value right for the price you play at those states. Okay? So let me look at perfect synchronous, okay? So pi is updated repeatedly, but max y in this is not. Okay, because I never actually go to the state that I didn't play. Okay? So these will converge to something, but it won't be to their actual expected discounted value if you played that. It will be to something else that depends on the random draws and stuff like that. Okay, so that's different now. The synchronous algorithm had to converge to Nash. This does not have to converge to Nash. Okay? So in a dynamic game, neither updating procedure guarantees converged policies that satisfy a best response condition. Okay? So let me show you what they look like, what the converged policies look like. This is from asynchronous updating. Okay, what you're seeing here is max, I think the 10th, the median, no, the 25th, the median, the 75th, and the minimum, just the quantiles from 100 things. You can see what's going on here. So the fact that you see these things going back and forth just means that there's a recurrent class that's not a singleton anymore. They're going through these cycles. They're going, it's converged. It's just going converged to a cycle. Okay, that's what's going on there. Okay.
Epsilon greedy, why don't you visit all states?
Pardon?
If you do epsilon greedy, wouldn't you visit all states with a certain probability?
If the epsilons go down fast enough, you won't. Okay, you won't. If the epsilons are stay epsilon, you never converge. Okay, because there's always an epsilon probability of hitting something else, right? So all of these models has epsilons converging to something. Okay. I think we did exponential, which is what's in Fudenberg and Levine also. Okay, so the quantiles oscillate, but look at where they are. So the perfect synchronous is, it's higher than 2, okay, but it's like 3, it's higher than 2, but the asynchronous is 9 or 10. Okay, there's a dramatic difference in these things, okay, from the converged policies point of view. The other thing that's sort of interesting is these sequences, this one, what's funny about what I thought was interesting, and I don't really have a formal proof of this, is it's going through a sequence. Both prices are going through the same sequence. That is, they're choosing the same price at the same iteration. Both algorithms. They never communicate with each other, okay? There is no communication of the algorithm. It's just through, learning the outcome from the play. There's no communication, okay? Still, if you were a authority, you might think they're talking to each other. I mean, they're playing exactly the same price all the time, okay? Okay. So the converged policies need not be optimal, as I said, even for the need not be optimal. You might want to ask the question, how far are they away from optimal? So is it conditional on what my competitor is doing. Am I doing something close to best response? Because if I was doing something close to best response, you might think there's not a reason to change. Okay? So here's the answer. These are fractions of the monopoly profits. So the asynchronous does pretty badly. So how do I do this? I just hold the other guy fixed at his policies, and I do a value function for this guy. Once I fix the other guy, it's just like doing a value function again. Okay? So you can see the asynchronous does pretty bad. The perfect synchronous does okay in the median. Okay, he loses 6% in the mean, 2% in the median. But there's these tail events. And the reason they happen is very clear. If I'm playing against somebody who's fixed, I can pretend I'm going to play high, then he plays next to me high, and then I cut the next time and make a ton of money. Okay, so if you get into one of those situations, and whether you do or not, it depends on the random draws, you can lose a lot of money or make a lot of money. Okay. Okay, now let's go on to online. Okay, so the real difference between offline and online is offline exploration is costless, essentially. And online, you set prices, you do the wrong prices, you lose money. Okay? Okay. The offline exploration, I said this at the beginning, but it increases if you start very high and if you have large epsilons. Okay? The reason this is being done is the training algorithm is trying to explore different policies before you go online. Okay, well, that's the whole goal of this thing. So doing a lot of exploration is generally thought to be a good thing. Okay? But not online. Okay, you never, so let me come back to this, but well, the convergence, the period of convergence, even in the synchronous algorithm in the dynamic game, you never converge until about 1 million iterations, ever, okay? So, we worked it out. If you got a new draw every 5 minutes every day, it would take 10 years before you converged. Is that clear? Nobody, no firm would leave an algorithm unmonitored for 10 years. I mean, it's just an absurd idea. Nobody would do that. Okay, the world changes too fast and stuff like that. Okay, good. So you get the idea that you can't really use converged things online. Okay. So once we go to the online game, there's uncertainty now because I don't know the policy when I go online. I don't know the policy of my competitors. Okay, and I don't really know the demand system. I might have some ideas. You shouldn't get me wrong, but I don't know the demand system. So there is uncertainty online, regardless of the offline training behavior. Okay, and the cost of error is going to limit experimentation and cause monitoring. You're going to monitor the algorithm. If it goes crazy, you're going to stop it. Okay. And it's going to force you to keep the number of states small because of the precision problem. Okay, now you're online. It's costly for every experiment. Okay, and if you experiment for a lot of states, you're going to be in trouble. And it's a econometric bias variance trade-off. Okay. Okay, and on the online focus, I'm going to consider just current profits, the first 10,000 periods of profits. So here's what we're going to do. We're going to start by computing a whole bunch of offline games. Each offline game will use different initial conditions and do different experimentation, but use the same demand function, costs, and learning rules. Okay. The offline games are stopped when the policies have converged. So we get 2 offline games, okay, from the same learning rule. Okay, and we just choose randomly one against the other. Okay. Then I'm going to play the 2 different converged policies against each other, okay, allowing for learning. Okay, so now we're online. Okay, I'm going to start with the trained policy. Okay, they're going to be different because they converge to different things. Okay, and I'm going to start with them and play them against each other online. Okay, and look at the first 10,000 period of profits. Okay. So there's a way to fix this up to make it a little bit better, which is costless, which is what happens in perfect synchronous is I update all these states, okay? But there are going to be states that communicate with these states, and I don't update them. And the fact that the profits at these states have changed means the values of the other states are not using that information. Is that clear? So I played something, I got some information at this state. State B communicates with state A, or state A communicates with state B. That means state B's value function isn't consistent with the new information on state A. Okay? So we do this thing called costless augmenting, which is we just keep in memory the prices the last time I hit each state. Okay? And I update all the states that communicate with this state. But that's just like one iteration. It's like value function iteration in dynamic games. It's one value function iteration. That's it, stop. Okay? And then we use that iteration as a return from the other state and just average it with what we had before from the other state. Okay? We call that augmented synchronous learning. Okay? That, you can do that. It doesn't require, why can you do it? Because it doesn't require any new information. I don't need to play anything again. Okay.
Just to clarify, you don't sweep the whole state space to this one value function iteration, but
only the ones I commute. So you can only do it for the ones that are in memory already. Yeah. So all of them that are in memory up to this state, we do it for, and then when we do it for more as more get. Yeah. Okay, so here we did this two ways. One, without allowing for online experimentation, and with allowing for online experimentation. Okay. How much time am I supposed to take? An hour or?
An hour and 15. So you have 35 minutes left.
I have a lot of time left, so people should ask questions relative to how much is in the paper. I have a lot of time left. We can talk about experience-based equilibrium if you like. Okay, so let me look. These are the results. The top line from the results is what you got offline. So that's the converged policy offline for each one of them. So that's the asynchronous converged policies, the average. There's the perfect synchronous converged policies, and the augmented perfect synchronous converged policies. So you can see two things that you should put a note on. One is when you go online, all the mean prices, actually the whole distribution of prices goes down pretty dramatic. It goes down no matter what you play, and it's extremely dramatic for the asynchronous algorithm. The prices get cut in half. Okay, they go down for everything: 3.91 to 3.10. Okay. 9.08 to 4.7, and now the asynchronous algorithm doesn't look so different from the synchronous algorithm anymore. Okay, and the augmented perfect synchronous is in the middle. So you conclude the limiting policies from offline play exaggerate the differences between online and competitive prices, and exaggerate the differences between algorithms. Okay, so at least in our example, okay? If you go to...
just to clarify, there's any more updating on...
No, here there isn't, and I'm going to show you on with in a second. Okay, that's the next one. But before I show you that, let me just show you what's going on. This happens in both of them, okay? So here's three pictures. These are typical price paths. Two things about these price paths. One, the two firms are setting different prices, unlike what happened in the training algorithm. Okay? Is that clear? So the price paths now, and everyone has a cycle in it. At least one firm is cycling. Is that clear? Moreover, this is the price passes from 500 to 520, and this is from 9,500 to 9,520. Okay? Nothing has stabilized, okay, in 10,000 iterations. Is that clear? So it never stabilized. So if you think that you're going to go to a training algorithm with fixed policies, okay, to a rest point of some form, it's just not going to happen. okay, on online stuff. So why do I bring this up so detailed? Because what I'm worried about, what the worry is, okay, is that people write all these papers on converged policies on training algorithms and then assume that's what happens on real platforms. Is that clear? And that's got all the authorities up in arms. Okay? Maybe all the authorities should be up in arms. You shouldn't get me wrong. And the best thing about this literature is they forced economists to start thinking about platform pricing. That's a good thing. Okay? But, you know, thinking that we're mimicking the real world by going to converged policies offline, training algorithms, is just the wrong way to think about it. Okay? That's not what we're doing. Okay?
Just to understand why the asynchronous algorithms that are successfully converged in the offline training session, and then why there's possibility.
This might converge, but it'll converge at 2 million iterations. And the 2 million iterations is just irrelevant. It's, you know, 20 years of data, every 5. 1 million is 10 years of a price point every 5 minutes. Okay, so, you know, this probably does converge. You shouldn't get me wrong. Okay, but the converged policies just aren't relevant for the things we want to study. That's what I'm trying to say. Okay. So price paths from online play differ markedly from those generated by limiting offline prices, and the difference continues throughout periods that are likely to be longer than the monitoring period. Okay. Okay. Online play with online learning. This is with online learning. The one with the results are sort of similar. Here we put in the paper in the AR. There's also downward sloping demand. Here we also put in downward sloping demand just to show you the differences. And you can see downward sloping demand isn't so far away from perfect synchronous. So this only assumes, it does synchronous updating, but it only assumes that demand is downward sloping. That's all it assumes. Okay? And you know, that's enough to change the result rather dramatically from asynchronous. Okay? Okay. So we did 2 digressions. Again, I said this is a paper with a simple point to make. But we did 2 digressions. The first thing we did is a 2-stage game. So the first stage, you choose your learning algorithm, and the second stage, you play the game. Is that clear? And we did 5 times 5 by 5 matrix. No learning. So no learning against asynchronous, synchronous, perfect synchronous, augmented synchronous, synchronous, asynchronous, getting there, and so on. Okay. So it's a 5 by 5 matrix. And the table identifies the best response. So this is the table. If you go through it, you'll see that the best responses are augmented, and you know the equilibrium would be augmented, or no learning, or asynchronous. Okay, so the 2 extremes are equilibria. Okay, so I mean this was the obvious thing to do. I didn't quite understand why we were doing it, so let me tell you. Because what's going to happen is you could simulate this offline for any environment you wanted to, okay? But we know that offline policies don't look like online policies, so that's not going to get you very far, okay? And if you started doing this online, okay, there's a much more difficult problem, which is determining what the other guy is playing and when I should switch what I'm playing, okay? And that's not here, okay? And that's what you would need to use this in any real world environment, okay? And so we haven't done that. So the other thing we did is we asked the following question. Could I hardline a program to give me collusion? Okay? So could I actually write a program which wasn't a learning algorithm, it was just a program which would induce the result that we colluded? Okay? So this is different now. It's different for a couple of reasons, but one of the reasons is the regulatory agents, so when they don't communicate with each other, when there's no bad actor in the environment, you can ask any lawyer you want, and they'll tell you you couldn't take this up as a collusion case. Because there's nothing going on that's collusive. Do you know, there's nothing, there's no intent on any part of the, okay? Now you might be able to, I don't know, okay? I asked a friend of mine who's a very reasonably famous, you know, antitrust lawyer. And the first stuff, he said, there's just no way anybody's going to ever, he knew about it. He said, there's no way anybody's going to get this through the courts. There's just, nobody will even try, okay? Here I don't know already, because now somebody's acting to do something, okay? It's not been in the courts, but maybe you could do it, okay? I just don't know, okay? Okay, so here's the one we do. You play 10 if 10 was played, here's I'm hardlining an algorithm to do the following, okay? I play 10 if 10 was played in the previous period, 10's the monopoly price, okay? If the rival undercuts, I play 2.57 in the next period, okay? If the rival price is higher than the firm's price, I play 3.14, okay? Unless 3.14 was played in the last period, in which case I play 10. So this is a two-period trigger, okay? Okay. By the way, in all of these learning things, we did it with random demand, with non-random demand, and you know, the results just aren't that different, okay? So I didn't go over it, but you can look in the paper, okay? Let's look at the two-firm results first, okay? So there's a trigger price guy, and there's the AI guy he's playing against. The AI's mean price, you can see what's going on, which is the more sophisticated the algorithm, the better everybody does. So if you're playing augmented perfect synchronous, you can figure out how to collude right away. Is that clear? And you know, the more sophisticated the algorithm, the quicker you can learn how to collude. Okay? So the maximum here, I think, is something like 166 point something. And these guys are getting very close. They're colluding after, you know, 250 periods, they're colluding already. Okay? 100% of the time. Okay? Okay, so now let's say now there were three firms. I want to worry about the fact that the state space is growing. So what I'm going to do is I'm going to do what comes from theory, which is I'm going to say the state space is my price last time and the minimum price of the other guy, which is maybe what I see, because that's the price that people bought at. Okay? So now I'm going to go to the three, whoops, there we go. Okay. Whoops. So now the results are way different. With three guys, okay, you can't keep the price above 3.4, and it doesn't matter how sophisticated the algorithm. In fact, the augmented perfect synchronous gets the lowest price. Doesn't collude anymore. Okay? So you might be able to hardline. Okay, so let me go to the conclusions, and then we can talk maybe more generally. So the design of the algorithm matters. I mean, it's sort of obvious, but and the implications of any design on the limiting policies from offline play differ from those from online play. So we shouldn't be using the limiting policies for offline play to mimic what happens in the real world. Okay. The online play mitigates the price elevation observed in the offline play, and online play generates price paths that are not similar to those observed from the offline play. You know, the thing we really need is a deeper investigation of how firms choose learning rules in different environments. Okay. I've talked to a few people who write these algorithms. They didn't tell me what was in the algorithm, but they were working for a firm. And you know, it's going to depend on the periodicity of purchases. I talked to a guy who once worked for Wayfair. You know, on each bed or sofa, whatever they were doing, they got one every 2 weeks. You know, this isn't enough to, you know, that matters. You've got to worry about pricing in that context where you only get an observation. Whereas, you know, if I'm pricing books on Amazon, I'm sure I get many every day. Okay? So that we just don't know. It's hard to figure this out because we don't we don't usually, they're proprietary. The algorithms are proprietary, so I can't uncover them, and maybe the way to look at it is to do empirical work and figure out what is consistent with the outcomes you observe in the algorithms. There does remain a question whether hardlining a different policy could induce collusion. Okay? We did one example. That doesn't mean anything, really. But, you know, what we want to bring out is the worry about collusion isn't about reinforcement learning algorithms. Okay? It's about somebody sitting down and writing an algorithm that's designed to induce collusion. The reinforcement learning algorithms have nothing in them that generates collusion necessarily. Okay, and in fact, we couldn't find it. From the simplest case where you think you might find it. Okay, we also did this with logit demand and stuff like that. Okay, so you know you might be worried about collusion, but not because of the reinforcement learning thing. If you're looking for collusion in the reinforcement learning thing, that's the wrong place to look. Okay, it's somewhere else, maybe, or maybe it's not. But whatever it is, it's somewhere else. That's really, it's a simple paper. It's one of my more simplest papers, actually. But that's all really I have to say. I'm happy to talk or answer questions or talk about something else, whatever you like.